Our first speaker for this morning is Jordan Stern. He's an active duty Air Force officer with 8 years of experience in various acquisition positions, including mission and project management and system engineering. Captain Stern received his master's in system engineering from AFIT and is currently pursuing a PhD in system engineering at Stevens. His research interests include space systems, architecting design, strategic decision making, and trade space exploration. And his talk today will be strategy dynamics and system of systems trade space exploration. So here you go, Jordan. Jordan, I'll turn it over to you.
Okay, thank you so much, and good morning to everyone, especially those who joined us from the West Coast at this very early hour. So today, as Mr. McDermott said, I will be presenting on strategy dynamics and systems trade space exploration. Make sure I'm actually on the slideshow here. So a quick overview of what we'll be discussing today. I'm going to go over the objectives of this research, the background for the problem area, introduce the methodology that we've developed, as well as the application case that we're using to assess this methodology and talk about the results from that application case, really focused on the method. And then we'll discuss those results as well as future work. So the objectives of this research are threefold. The first is to develop and demonstrate a conceptual design methodology that incorporates collaborative system strategy dynamics in a trade space exploration. This is really geared towards collaborative systems, which many of us refer to as system of systems, or collaborative systems are a type of those. And the sub-objective here is to yield constituent systems that are robust to the dissolution of the system of systems, which actually then promotes its formation and stability because the various design actors don't lose everything if the program or the project ends up not completing successfully. A secondary objective is to determine how economic variables, and we'll talk about what those are a little bit later, impact constituent system technical implementations, as well as assess the suitability or the goodness of our proposed methodology for performing such analyses and for performing analyses that include economic variables in general. And the third objective is to determine the impacts of operational uncertainty on the expected value of designs that are generated using our proposed methodology, and understand the interaction between a low-level kind of traditional uncertainty that would affect cost, schedule, performance type elements of programs, as well as the higher level issue of strategic stability, which is what this research is primarily focused on. So just a little bit of background. We will be using a space systems application case, and the space economy right now is going through quite a bit of growth and transformation that is creating opportunities for collaborative systems that enhance value for the constituent system owners or operators. As we all know, though, system formation requires investments to enable an operation. And there also is temptation to maximize efficiency by reducing functionality that is redundant across a formed system of systems. So, or one system provides functionality to the others in the system, those others may be tempted to eliminate that functionality in the aim of maximizing efficiency. However, this creates a situation where a failed system of systems will result in non-recoverable interoperability costs and expensive modifications or program delays to adapt the systems for independent operation. So this means that we require methods which objectively and consistently assess designs, the individual constituent designs, for suitability in a collaborative systems context. A lot of work has been done in this area over the last several decades, but it's largely focused on combining the objectives of the various constituents, either by applying some kind of multi-objective weighting or assuming some independent global system of system objectives. And while many of these works, or some of them anyways, do acknowledge that there needs to be some upside benefit for each of the constituent systems to collaborate, that existence of upside is not sufficient to determine that participation in a collaborative system is rational for each of the design actors. And we're going to talk about that in just a minute. So fortunately, game theory does provide us the tools for strategy selection in a multi-decision maker problem. That's exactly what it's intended to do. And games can be used to model multi-actor decisions in engineering design, and recent research has demonstrated this. In the context of the research cited there, as well as this research, we're using the canonical stag hunt game to model the strategy dynamics in a system of system design. In the stag hunt game, the two actors have a choice between either collaborating on a efficient or payoff dominant strategy in which they receive more than they would through independent operations, or pursuing an independent strategy. In this example, collaboration is represented by stag hunting, and independent operations is represented by hare hunting. So if they collaborate and they're successful, they get a higher payoff. If they pursue an independent solution, it's a lower payoff. But it's a sure thing. There is this diagonal case where one design actor or one constituent collaborates and the other does not. And in that case, in our kind of toy example here in the stag hunt game, someone who pursues stag hunting but does not receive reciprocated collaboration ends up with a lower payoff than they would have if they had pursued hare hunting originally, and the defecting hare hunter actually receives a higher payoff. And that may not always be the case in a system of system context, but it's a close analogy. In these types of games, we can use a measure called the weighted average log measure of risk dominance, denoted here by the italic R, which indicates the risk dominant strategy. That is the one with the largest basin of attraction, or that is, in simple terms, the least risky. And an R value lower than 0 indicates the dominance of the collaborative strategy. That is, that the stag hunting strategy is actually the least risky based on the payoffs. So we can transform the payoffs in that table to the plot in the upper right-hand corner, which shows the expected value of one actor, we'll call actor I, versus the probability of the other actor selecting a particular strategy. In this case, the collaborative strategy represented by size of J. And this expected value is for both of the actor I strategies, both hare and stag. And we can see that those strategies have a crossover point in this particular case at a value of 2/3. And using this value that we call the normalized deviation loss, along with some influence weights that are derived from a matrix that we won't talk about here, we can compute the R value. And in this particular case, which is very simple, the R value is 0.69, indicating that the independent strategy, which is hare hunting, is risk dominant. It is less risky. And you can kind of intuitively gather that from the plot, that there's this larger probability range over which it yields a greater expected value. So we can mesh this with the engineering design domain by introducing designs for each of the actors. So assume that on the previous two charts, a hare hunter would bring dogs, and a stag hunter would, who's planning on successfully collaborating with another stag hunter, would bring a spear. And set aside the realism of the designs if you happen to get under yourself, we can introduce a third design, the bow, which is strictly worse than dogs for hare hunting and than spear for stag hunting. But acts as kind of a bet hedging because in a unsuccessful or a failed collaboration stag hunt, the stag hunter does receive some payoff. They can have some expectation of being successful in a stag hunt with a bow by themselves. So if both hunters, both system actors select the bow, then the R value is decreased to negative 0.69, meaning that the bow design changes the strategy dynamics such that collaboration is risk and payoff dominant, and all other things equal, meaning that it should be selected as the strategy for both actors. So we take these concepts and merge them into a two-phase Tradespace exploration that implements risk dominance as a criterion in a multi-attribute heuristic search. In this case, we were using a genetic algorithm. And we had two objectives: maximize the net present value for each system and minimize R. So we perform this, as I said, in two phases. The first phase performs kind of a traditional Tradespace exploration using a genetic algorithm, searching for the value maximizing independent designs, which would be analogous to the hare strategy for each actor. Then we use that value to perform the second phase of the Tradespace exploration, where we simulate the system of system designs, both under successful collaboration and under failed collaboration, where one of the other systems is not participating. And then we determine the net present value in those circumstances. Then we have all the information we need to compute R and obviously to determine the value of each architecture. Our application case assesses collaboration between two hypothetical commercial space systems. The first is an Earth observation system, and the second is a satellite communication system that provides broadband internet services. Each system can operate entirely independent of the other, such as many legacy systems do today. And collaboration occurs when both implement interoperable inter-satellite links. The SATCOM system then performs EO command and data transport for a fee. So they're sending requests for images, for example, to the spacecraft, mission tasking basically, and then also taking the mission data, which would be the imagery data, back down to the ground. The EO system data value is then increased because the latency decreases. You can shorten that time gap between when a tasking is sent out and when the data is received. And we evaluate both these architectures for a 5-year mission duration. The top of this chart here just shows a graphic of what I just described. And failure to coordinate on the collaborative system, in this particular case, results in unrecouped interoperability investments for both systems. There's some expense to implement those interoperable inter-satellite links. And similarly, there's a temptation, as I talked about in the early charts, for the Earth observation system to not build any organic ground stations of their own. So they rely entirely on the SATCOM system in order to move their data and to receive commands. In that case, if collaboration fails, then they're left without organic data transport capabilities. Our simulations require them to lease ground stations at a higher cost than they would have incurred had they built their own. For our Earth observation system, we conducted evaluations over the Tradespace depicted in the table, and we evaluated net present value through a combination of simulation and analysis. Revenue came strictly from the sales of imagery, which was a function of resolution of that imagery and the latency of the data, and we estimated cost using a parametric cost estimate. The SATCOM system was evaluated over the Tradespace depicted in the table here as well, and we evaluated net present value, again in this case, through simulation and analysis, and the communication revenue was a function of system capacity and a subscriber base that grew over time following a sigmoid curve. Cost, again, was estimated using a parametric cost estimate. And we performed our evaluation in 3 steps, and I'm going to talk about the first one here. The first analysis looked at fixed economic variables and a deterministic schedule, because those are the things that we're going to vary later on. So we had a fixed data transport fee that was set at $10 million a month. It went from the Earth observation system to the SATCOM system for each month in which data transport services were provided by the SATCOM system. Under this arrangement, our top independent Earth observation system design, remember this is operating independently of the SATCOM system, there's no system of systems here, was comprised of 3 planes, 3 satellites per plane with a 1-meter aperture, operating at a fairly low altitude of 400 kilometers, and had 3 ground stations for an NPV of about $347 million after that 5 years of operations. The top independent SATCOM design was 41 planes, 80 satellites per plane, with fairly narrow beams, a 40-degree minimum elevation angle, 32 transmit channels that were 500 megahertz with 1 watt transmit power per channel, an 8 PSK modulation scheme with a 2/3 convolution rate, and had a net present value of about $9 billion. So then we can conduct the second phase of our analysis, and here we're looking for those collaborative system of systems. In this case, all Pareto-efficient collaborative SATCOM system designs were identical to the best independent design that I talked about on the last chart, aside from the fact that they incorporated this interoperable inter-satellite links. The EO system designs varied over a relatively small range, and they basically traded maximum NPV for reductions in R, which were achieved by first decreasing the investment costs in the system and then adding organic communication paths. So that's exemplified best by looking at designs 1 and 3 in the table below. So in design 1, the collaborative EO system design adds 3 satellites by adding additional satellite per plane, and eliminates ground stations in order to maximize efficiency, as I was saying before, which doubles the net present value. And in this case, the R value still does favor collaboration, but we can make collaboration more favorable by eliminating some of those satellites, which reduces investment costs, and then adding 3 ground stations, which adds that organic capability to operate independent of the SATCOM system should there be some coordination failure. While that does reduce the net present value quite substantially, it also reduces the R value because, as we'll see in following charts, it reduces the downside risk of failed collaboration much more than it reduces the upside. These two charts show for that highest NPV collaborative design where the trade-off is for each of the system owners. So you can see that for the Earth observation system on the left-hand side, that U value, that crossover point between the two strategies and their corresponding best designs, happens for a fairly high probability of SATCOM collaborating, meaning there's a large region where the Earth observation system owner expects some loss. Conversely, for the SATCOM system owner, that crossover point happens at a very low probability of Earth observation system collaboration, meaning they have relatively little to lose and much to gain by collaborating. And that is what, in fact, creates the dynamics that favor collaboration in this particular case. So looking at just the Earth observation system owners' designs and strategies, since collaboration is largely a function of what they end up doing, giving them the most to lose, we can see that design 3, which had the 3 ground stations represented by the magenta line, trades some upside benefit for a substantial reduction in downside loss, essentially trading efficiency for robustness. And that's a theme that we'll see throughout. So our extended application case, which then picks up where the last one left off, extends the example through implementing a cost share on the Earth observation system's interoperability unique non-recurring costs. So basically their development costs for those inter-satellite links. And varies the fee, that data transport fee that was fixed at $10 million from $1 to $20 million. And we did this because we saw that the Earth observation system owner could lose significant investment if collaboration failed. So shifting some of that risk to SATCOM and then rewarding them with a higher fee potentially could improve the collaborative dynamics. And this is done by ensuring that SATCOM's portion of the cost share is not recoverable if they unilaterally select the independent strategy. Essentially, we're assuming that at simulation start, there's a contract in place that enforces that. And not surprisingly, inclusion of the economic variables results in many, many Pareto efficient designs for a given technical implementation. So you can imagine that if we were to pick one of the architectures that I talked about earlier, and then just vary the fee from $1 million to $20 million, that would create advantage financially for one of the other design actors. And that's the case for every technical implementation. In this case, inclusion of R provides an objective criterion for discriminating between these solutions. So rather than having a situation where both design actors are just simply trying to negotiate themselves into their best possible position, benefiting their optimistic net present value, we can select solutions based on those which most strongly favor collaborative dynamics. And then after performing that analysis, we model schedule uncertainty by performing Monte Carlo simulation on a few of the better performing designs that came out of that analysis with the inclusion of economic variables. So here I'm just going to talk about some of those designs that were on or near the Pareto front after we considered economic design variables. And these were selected based on basically coverage of that front, as well as a little bit of technical diversity so that we can see what happens when we model schedule uncertainty. So of course we selected the minimum R design, that design that drove the R value the absolute lowest, as well as the maximum NPV designs for both actors, EO and SATCOM, that still maintained favorable collaborative dynamics. And then we selected a few other designs that were kind of somewhere in between, some that were highly efficient, that maximized value, but distributed the value differently than those top 3 designs, and then some that were less efficient, but incorporated some robustness features that we want to see how they would be affected when we added some schedule uncertainty. So the results of the Monte Carlo simulations are presented on this chart. On the left-hand side, we have a bar chart that represents the expected net present value under successful collaboration for all 1,000 trials of the Monte Carlo simulations for each of those designs that I talked about in the last chart. The y-axes on either side are scaled so that the independent net present value under schedule uncertainty is represented by the black line for both system designs. So we can see that the designs on the far left, the min-R design, the max EO MPV, and max SATCOM MPV designs, all have one or the other of the actors expected in PV under successful collaboration that is below what they would get in the independent case. So this is like going back to the beginning of the presentation, getting less for stag hunting than you would for hare hunting. So in those cases, R is undefined, and the rational strategy for both actors is to pursue an independent system design. So we can see that there's some flaws with just kind of ham-fistedly applying our risk dominance criterion without consideration of other factors. However, there are several other designs that do very well. And those are designs that were efficient, but also distributed the benefits of collaboration a little more evenly between the design actors, leaving them some insurance against an uncertainty that wasn't factored in to the initial analyses. So the results all throughout do show this consistent trade between collective and individual efficiency and system robustness. And that is probably exemplified best by the addition of ground stations on the Earth observation system in order to lower that R value, which reduces net present value in the optimistic case where we assume collaboration is successful, but also reduces downside and incentivizes the Earth observation system owner to actually kind of more forcefully pursue collaboration, knowing that they don't lose everything if they take that route. However, the Monte Carlo simulations did reveal a limitation in the current implementation of this work, which uses complete information games. That's because strategy selection is entirely dependent on the payoffs. There's no other factors that go into it. And small payoff changes or payoff uncertainties can have large impacts on equilibrium selection. So we saw that consequently, design combinations which are very robust, apparently, to strategic level coordination failure may actually be quite fragile to operational uncertainty. And in this particular application case, that's because there's this very low downside risk for SATCOM that paradoxically exacerbates the problem because only a slight upside is required for collaboration to be strongly favored for that design actor, meaning that a perturbation that wasn't considered in the initial analysis can totally change the strategy dynamics such that that actor switches strategies. And we'll address this issue with future work. But the way we plan on addressing that issue and other issues that weren't discussed here is with concepts from Bayesian games. So Bayesian games essentially apply a probability distribution of the payoffs of players, and there's many different ways kind of that can be done, or frames from which that can be done. And that would enable us to model payoff uncertainty a lot more efficiently than Monte Carlo simulation. We weren't able to perform Monte Carlo on all the outputs of the Tradespace exploration exercise. It would have just simply taken too long, as well as actually enable us to really optimize designs with that kind of a priori consideration of the uncertainty that would traditionally be considered. It also allows us to model varying degrees of managerial independence by incorporating something called team reasoning that I'm not going to talk about extensively here, but basically allows us to model the reliability of the various players based on their real-world ability to make their own decisions. So, for example, two commercial entities that have no ties to one another have 100% managerial independence, whereas maybe in a joint program within the Department of Defense, for example, the executive officers for the various programs have some managerial independence, but they are ultimately responsible to a higher authority, which changes the dynamic somewhat. So that concludes my presentation, and at this point, I'd be glad to take any questions that folks have.
Thank you, Jordan, your presentation. So we had one question from Xiaomei Yu. Sorry if I mispronounced that. Which modeling tools are used for this work?
Okay, sure. Yeah. So to do the simulations of the kind of the spacecraft dynamics, we used an open source tool called ORCID, which is written in Java, I believe, but we used a Python wrapper. In order to do the optimizations, the generic algorithm we used for the Tradespace exploration was implemented in DEEP, distributed evolutionary algorithms in Python, which is open source. And then obviously we wrote quite a bit of our own code to do the cost estimation and some of the other more analytical stuff. But the most complex parts are in open source libraries.
Thank you. I'll remind people to ask questions in the Q&A if you have them. Jordan, the second question actually comes from me. What can you say about the case where the EO satellite decides to permanently divest of a capability due to a decision to depend on the SATCOM for collaboration? Would you model that as a second order game?
Yeah, so I think what you're talking about is like, they don't have any ground stations or whatever, right? Because they're
Yeah.
entirely dependent on SATCOM. So that is kind of what we were modeling. Our initial analysis assumed that if the Earth observation system owner did completely divest of capabilities, that they were without any communications functionality, meaning that they would essentially have just sunk all their money into an investment and get nothing out of it. What we assumed in the results that are presented here is that if that were the case, they would have to lease ground stations. And we use some publicly available numbers to compute those expenses. So we assume that the mission does go on, but we did not assess a second order decision of whether or not after collaboration breaks down to start building ground stations, if you will. We had assumed that decision has passed, and now ground station leases are automatically implemented as a to recover what can be recovered, basically. So yeah, otherwise, if we were to do something different, we would have to assume some line in the sand in terms of schedule in which that decision would be made, and we weren't modeling things to that fidelity.
Follow up to that. Have you looked at the case where, for example, a decision made to collaborate with that SATCOM provider perhaps prevents them from collaborating with a lower cost provider in the future?
No, we haven't looked at that. I know Dr. Verma is on, and I've had discussions with him about this work in the past, and there are all kinds of directions we could go, including looking at scenarios like that are kind of semi-competitive, or looking at scenarios that are more competitive than that. One of the things similar to that we did consider, though, it didn't model, was that in our approach, we don't really take into account the loading of the various systems, for example, which could change over time. It may be, the flip side of the question you're asking is it may be more beneficial for SATCOM to devote resources at a particular point in time over a particular region to serving ground customers, right, for example. So yeah, we didn't look at kind of all those permutations, though.
Okay. Yeah, maybe some future work. So another question from Paul Grogan. He says, great job, Jordan. What change in the proposed methodology would you make if you wanted to augment existing systems rather than pursue greenfield designs for collaborative opportunities?
Right. So I think in terms of the methodology itself, not much would change aside from the fact that certain things would be more certain, right? Particular design parameters, for example, that weren't under evaluation for change in the future, which would in some ways make things the results, I would say, better because we'd have more knowledge about a reality, and would reduce some of the sources of uncertainty potentially. So for example, in this case, in our initial analysis, we assumed that both programs would begin fielding their platforms at the same time, and that's where that schedule uncertainty kind of played in, is in those schedules becoming disjointed if one or the other or both experience delays. Whereas in an augmentation type scenario, you wouldn't have to deal with that problem. But I don't think methodologically anything other than just the details of the implementation would change.
Okay, thank you. I guess one other maybe comment or at least interesting note I would add, particularly in this domain, would be possibly if you had a third player in the game that was an infrastructure player.
Right.
So somebody like depending on Amazon Web Services for satellite downlink data, how would that change your methodology?
Yeah, so I think I'd have to think about that a little more in terms of methodologically how it would change things, how we would factor that third player in. Are they part of a sub game for one of the players? Are they involved in the overall game. There's probably different ways to handle that based on the details. I'd have to give it a little more thought though, and I'll do that and get back to you. AWS pricing is actually what we used for those ground station leases, but it wasn't really part of the game. Like I said, it was deterministic. If collaboration fails, you have no ground stations, you must use AWS. But yeah, incorporating that as part of the decision space initially, it would be interesting. I have to give more thought about how to do that.
I'm sure Dr. Grogan will be interested in that.
Yeah.
All right, so right on time. That's the finish of the questions. I want to thank you, Jordan. Very interesting.
Thank you so much for moderating.
It's too bad we're virtual. We can't all clap for you and have you hear it.
That's okay. It's quite all right. Thank you.